Okay, so as I have been discussing, basically the Doppler Shift Attenuation methods of measuring the nuclear level lifetime. Now we have talked about two methods. One is recoil distance method and another is Doppler Shift Attenuation method. Now what we do in both these techniques, please look carefully, we take a very thin target. Why? What is the need? What we want is that beam should fall on the target, okay, and then after reaction, the recoiling nuclei along with the particles, they should be emitted. Now you must be wondering, sir, if this thing happens in the air, then they will be blocked by the air and we will not be able to observe anything. They will be immediately stopped. So to make life simple, we will do this experiment in a vacuum chamber. That means this entire setup will be inside a vacuum chamber. Fine. And there will be a neat hole over here, something from which the beam will fall on the target. Okay. What happens is that there is this metal cage, something like this. So from this the beam comes and directly this is the target chamber. It is coupled with the beam pipe. Okay, so no obstruction. Beam comes and hits the target. Okay, now what happens is that as a result of the reaction, the recoiling nuclei and particles, they move, and while moving they decay gamma. Now in the recoil distance method, what we do is the following. We allow the recoiling nuclei to move in vacuum, and after some time there is a thick metal plunger. So they move over here and this distance is d, say, and after that they are stopped in this metal plunger. So what will we observe? Two things we will observe. Number one, while moving, is there any obstruction? No obstruction. So they move at a constant velocity, right? And this we can find from the kinematics. We know the incident energy, right? Projectile mass, target mass. It's very simple. Now, so they will be moving at constant velocity. Now, while moving at constant velocity, if the recoiling nuclei, they emit a gamma ray, what will happen? We will observe that while, suppose, the recoiling nuclei is moving like this, and while moving it emits a gamma ray. Now if we observe this gamma ray at an angle theta from the recoiling nuclei, then the energy of this gamma ray will be E gamma equal to original energy E0 1 plus beta cos theta. Now this is a very basic approximation, zeroth approximation I am considering. You have to actually use the entire relativistic equation. Okay, fine. Now you see in this recoil distance method, this is vacuum, so they are moving at a constant velocity, beta is fixed, and while moving, if they emit gamma ray, we will just observe a peak. What we will observe is this shifted peak, right? Now suppose out of 100, 40 decays in between and some of them decay after entering the plunger, something like that. Then what will happen? The ones which decay after entering the plunger, it means they are stopped. Okay, then what we will observe? We will observe the unshifted peak. Why? Since they are stopped, V is equal to 0. Right? So this is what we will observe in the recoil distance measurement. Now look here, I am assuming equal intensity, which is not the case. Actually this changes. The intensity changes. And from this, we will be able to extract the lifetime. Basically the distance it moves. Okay, we will be able to extract the lifetime of the recoiling nuclei from the lifetime of the particular level from where the gamma is being emitted. So this is the technique of RDM and this is what you observe. I have discussed about this, right? Now in DSAM, what we do, we use a different philosophy. This time what we are doing is the following. Instead of keeping a gap over here, now what we do is no gap, but thin target followed by a very thick backing, and the backing medium is chosen such that whatever they recoil, afterwards they will be stopped in the backing. Now what will happen? What happens is this: after the formation, it starts moving, but there is no vacuum now, so it starts moving in the backing medium. Now think of the iron, it is slowly moving, so this means there are collisions, and as a result of the collisions, it will slowly, its velocity will decrease, and during the decreasing velocity, if it emits a gamma ray, what will happen? We will observe the gamma ray with a decreased velocity. Okay, that means the shifted peak in the previous case here, E gamma is equal to E0 1 plus beta cos theta. Here beta was fixed, right, in the RDM method, since it was constant moving in the medium. But here, since it is constantly colliding because of the collisions, it is losing energy, so beta will vary. Okay, and as a result, what we will observe is something like this. Here, this is the unshifted case, this is the fully shifted case, and we will observe what in between. And now this is a very absurd scenario where all the intensities are same, but in reality, all the intensities are not same. So what we observe is something like this. You see, what we observe is something like this. So this is unshifted part, and this is entirely shifted part. Now if you observe at some other angle, it is possible to observe something like this as well. Okay, so and what is this thing? This is the line shape, this shaded part. You see, here also, this is the line shape. Now there are two ways to do the estimation. One is to try to simulate this line shape, and by doing so, now you see what is happening. The recoiling nuclei is slowly moving in the medium, colliding, and if we know the physics of these collisions, how it is moving, how it is slowing down, then from the characteristic slowing down time, we can find out the level lifetime of the nucleus from which the gamma ray is emitted. This is the actual principle. Okay. Now you see there are two ways of doing this estimation. One is we try to simulate the entire line shape, or number two is we just calculate the entire centroid of this and then calculate it theoretically. So one is centroid shift method, another is line shape calculation. There are two ways of doing this. Any questions? So basically I have talked about RDM and DSAM, right? Roughly. Now RDM, what's the range of lifetimes? 10 to the power minus 8 seconds to 10 to the power minus 12 seconds, roughly. What about DSAM? Lower, 10 to the power minus 12 to 10 to the power minus 14 seconds. So these two are very important techniques. And below 10 to the power and above, actually above 10 to the power minus 8 seconds or so, we use the electronic timing techniques, right? Using TAC and all that stuff that I have discussed. The fast low coincidence circuits. Okay, so this is the entire philosophy. You remember this. So this is very interesting. You see, so when we are unable to use the electronic circuits, remember, one of the important reasons for not using electronics is that they have inherent noise, and that will be limiting factor. So in order to overcome this issue, we are now using the Doppler shift methods over here. Now this is not the first time that we have used Doppler shift method. In case of a star, when the star is rotating, if we observe the gamma ray or photons from the part which is moving away or moving towards us, there is a Doppler shift. Consider the gas molecules or atoms and molecules inside the star. They are moving in a thermal motion. Even observing the Doppler broadening, we will be able to get information from them. right? So it's a very important tool, this Doppler shift. And here I am just showing you qualitatively how we will be able to estimate the nuclear level lifetime using the Doppler shift method. Okay. Any more question?
So এখানে RDM বা DSAM এর পেছনে যেটা করা হয় প্লাঞ্জারটা যেটা করা হয় ওইটা স্যার এই থিকনেসটা কার উপর নির্ভর করে মানে কতটা
Plunger, I have to choose the plunger such a way that it has to stop. Okay. And remember, in RDM we can change the plunger to target distance. The D is changed, and it is very sensitive equipment. Why? You see, it's a very small. You are considering 10 to the power minus 8 to minus 12 seconds, and the distance, the two setup must be very parallel. It's a very, what will I say? It has to be. It's a very delicate instrument. Okay, they must be parallel. If there is slightly unparallel, then your entire experimental result will not be very reliable. Okay. So, if I ask you differences between RDM, DSAM, no medium, medium over there, right? Only two peaks, entirely shifted and entirely unshifted. And here there is a range of shapes. Okay, but both use the Doppler shift method. And most importantly, the third difference, this is range minus 8 to minus 12, and that is minus 12 to minus 14 and below, like that. So this is very important, write it down. I'm not writing it down, you can find it. Any more questions? So I have talked about the line shape also, the centroid shift method.